Hello, and a very warm welcome to episode 4 of ChemEdge Conversations. I'm your host, Ravi Shankar, and on behalf of my team, it's our pleasure to welcome a very special guest, Dr. Colin Hale, to our show.
Pleased to meet you.
Nice to meet you too. So, Colin has been a long-standing stalwart of the Department of Chemical Engineering here at Imperial College. Having completed both his undergraduate and postgraduate studies with flying colours, he now holds the position of Senior Teaching Fellow in the Department of Chemical Engineering. Prior to his appointment as a Senior Teaching Fellow, he worked as a Research Fellow specializing in multi-phase flows for both the upstream and downstream oil and gas industries, as well as nuclear thermal hydraulics. He developed pioneering techniques for X-ray tomographic imaging of multi-phase flows in pipelines, which techniques are actually being deployed in both the petrochemical industry as well as oil refining. From a teaching perspective, in 2011 he was nominated for the Faculty of Engineering Excellence in Teaching Award, and just this year he received the prestigious President's Award for Excellence in Teaching from Imperial College, which is an outstanding achievement, and congratulations.
Oh, thank you very much.
That's wonderful. Aside from his wealth of knowledge in science and engineering, I think it's safe to say that he's one of the most, if not the most, loved people in our department. I mean, a true gentleman, friend to all, and a source of moral support for all the staff and students in our department. Never too busy for a friendly chat or away from the pilot plant control room, which he spends just a bit of time now and then, would you say, Colin?
A little bit of time.
Yeah, just a little bit of time. So with that, it's our pleasure to welcome Colin onto the show, and we're looking forward to an exciting conversation. So thank you for coming.
Thank you.
So, as we mentioned, you've been an integral member of the department for a long time, having studied your undergraduate studies here, then PhD, and now Senior Teaching Fellow. So could you tell us a little bit about your current role in the department?
Okay, so my current role, as you've pointed out, is Senior Teaching Fellow within the department. The main part of my role actually is also managing the pilot plant facilities, and our interaction with our sponsors, ABB, and also teaching our students. So that's a lot of my day-to-day role. In addition to that, I do lecturing for some of the first-year courses, some third-year project supervision, and part-time consultant for the fourth years for their design projects, for example.
Okay, that's interesting. So, alongside your teaching, one of your primary focuses would be handling the commissioning and operation of the ABB carbon capture pilot plant, whose control room we're sitting in right now. And for our audience members who aren't aware, our department is actually the only chemical engineering department in the UK which can boast a state-of-the-art, fully functioning chemical plant of this scale, and one of the very few in the world who provide students hands-on training with a chemical plant during their undergraduate studies. So could you provide us a bit of an overview about the plant, its functionality, and when it was constructed?
Okay, so the process itself is a pilot scale carbon capture facility, so it's replicating the sorts of process that you would use for example, removing carbon dioxide from the gases of a coal-fired power station or a gas-fired power station. The process itself is very similar to the ones used in upstream oil and gas production, particularly for something called gas sweetening, where you purify the gases that you obtain from reservoirs. In terms of the scale of this process, as you'll see later when we go around the plant area, this runs over 4 floors of the building. It will process around 500 tons per year of carbon dioxide. Wow. To put that in perspective a little bit, very roughly, every one of us has a carbon footprint of around 10 tons per person per year. So this would process equivalent to the carbon footprint for 50 people.
Wow, okay.
In terms of the scale of this facility relative to other facilities, this one will process around 500 tons per year. It's equivalent in height to about 3 double-decker buses stacked on top of each other. Full-size ones are operating to process 1 million or 1.5 million tons per year. But although this is a smaller scale facility, all of the equipment on here, including the control room that you're currently sat in, and the equipment you'll see out on the plant area, is full industrial grade equipment. And that's actually what differentiates these facilities from any other facility in the world, and actually makes it quite unique.
Oh. They're definitely very interesting, and I think safe to say, I mean, it is a feat of engineering to put together something on this scale, especially with such a complicated process. What would you say was one of the biggest challenges that your team had to face during the construction of this plant that probably comes to mind?
Okay, so in terms of the construction itself, there was actually some equipment in the area that we'll see later previously. So one of the first challenges was actually to remove that equipment because it got to the end of its lifetime. That had been put in 1970. And one of the decisions was made to replace that equipment and actually improve on it and enhance it quite a lot. So things like the control room that we're currently sat in wasn't initially on this floor. That was one of the aims of the project.
I see.
In terms of the overall project, we had to remove the old equipment, so that we were involved in the decommissioning aspects of that. Then we had to coordinate quite a lot of suppliers and designers and electrical people, safety people, mechanical engineers, civil engineers, so that we could manage to get the process built within a reasonable period of time. Because one of the main challenges for us was to ensure that the facilities were available to students more or less continuously. So one batch of students finished off on the old process plant. Literally the day after the final group finished on that process, what we then had to do was start to decommission the equipment.
Okay.
And then to minimise time, we needed to ensure that within around a year and a half, this facility was available for the next group of students, so that we didn't disrupt the teaching for our students as much as possible. In terms of putting the facility in, that meant that we were involved in the design all the way through the process, but also in the construction and the commissioning phases. The timeline slipped slightly, actually, during the course of the thing, and part of the reason for that was that some of the bigger equipment got manufactured in Italy, so that got shipped at a particular time. That got delayed on when it came from Italy, partly because some of the instrumentation that was required to be on the process couldn't be provided from a factory in Germany. And the reason that that couldn't be provided was because some of the electronics from Japan that were used for those instruments weren't available. And the reason that that wasn't available actually was the plant was constructed around 2011, 2012. If you think back, that was around the time of the tsunami in Japan. So actually the factory in Japan had got wiped out, and there was a worldwide shortage of electronics. So that meant I had a lot of knock-on effects from that one event. It's something you couldn't really plan for.
I mean,
on
it's
a process of this scale, actually.
I mean,
no way you could plan for it.
It was a natural disaster, so something
exactly.
that you can't really plan for.
Yeah.
I see. But despite that, you were able to see it through and fully construct and commission the plant, and now it's up and running. Would you say, having seen it from start to finish, this is probably the biggest achievement of your career?
In terms of putting this facility into place, I think, certainly one of the biggest achievements. I mean, not just for me, but also these types of facilities only really get constructed once every 20 or 30 years. So it quite literally is a once-in-a-lifetime opportunity that I've been involved in terms of gearing up a facility of this type.
And how did you actually become involved with the construction in the first place? Was it because your research interests or your expertise in industry lined up with what the project needed at the time, or?
Okay, so the way that I got involved in the project initially was the area that I worked on as a research fellow was related to the upstream oil and gas industry, as you pointed out. So my work was experimental work. So I was actually working on quite a large-scale facility previously. So I had a lot of experience with larger scale facilities. In the case of that particular rig that we were working on, that was around 3,000 litres of liquid, oil, gas and air at quite high pressures. And the pipeline itself was over 40 metres long. So fairly big scale facility. That meant I had a lot of experience dealing with heavy pieces of equipment, lifting them, moving them.
Sure.
As a consequence of that, the department asked if I could spend some time to decommission the old equipment that was in the plant area.
Mm-hmm.
So that's when I initially got involved. So I got involved in the decommissioning project for that,
Mm-hmm.
and planned it out. And then with our workshop team and our electronics guys, we were involved in taking out all of that equipment to prepare the area ready for the building workers who came in to refurbish the internal area.
Wow.
And then at that point, I'd taken all the things out, and I felt a bit guilty really, because actually I'd taken away the facilities our old students were working on,
Yeah.
and I wanted to make sure that they could also have the benefit of the facilities we were putting in place. So it followed on from there.
The quick turnaround.
A natural progression, actually.
Okay, that's really interesting. And from the plant as a whole, how would you say that the department uses this for both research and educational purposes?
Okay, so the facility itself is geared up predominantly for teaching, and that was one of the main aims from very early on.
Mm-hmm.
So now all of our undergraduate students come through the plant to gain the experience of working on a fairly large-scale industrial process. When we're not, or when I'm not teaching those students, we also teach summer school students from other countries. So we now get students coming across from America, from China,
Wow.
from Korea,
Mm-hmm.
some from Mexico. When I'm not doing those exercises with those students, we do training for engineers from outside as part of our sponsorship agreement.
Mm-hmm.
So that means that I know that a lot of the things we do on the plant are actually directly relevant to employers, and I think that's a really good benefit for our students, because that means the skill set they pick up will be of direct benefit to them later on.
Absolutely.
So that's the teaching side, and as you can probably imagine, that takes up quite a lot of the time on the plant, because these days it's just under 1,000 students every year go through the control room to do things on the plant. As far as the research things, some of the bits that we've been doing are industrially related. So actually we've been doing some things related to what's called Industry 4.0. Now what that means is that's about how you can use internet connectivity but on a process plant. So you can pull off data but not just look at it locally, maybe look at it in other countries or globally. And the aim of that is because if you can integrate industrial processes and use that data effectively, then actually that gives you enhancements in performance on process plants.
I see.
So some of the things we've done on that have been looking at how we can improve what's called preventative maintenance. We were actually the first site anywhere on a plant to do tests on this. It's been done in the laboratories before, for sure. When we did the initial test for that, we actually had a group of engineers in Bangalore in India. They were connecting into our system. They were giving us diagnostic information in real time.
Wow. Okay.
So
that's
we can
amazing.
call upon experts from other areas, and we've been doing some further things based on that as well.
Oh, that's really interesting. So it's great to see that the plant is being used, both aspects, quite heavily for teaching, but as well as for research as well. And that's one thing that we like to emphasize, that for any prospective students who are considering studying here in the department, one of the core principles that frames our teaching excellence in the department is we try to achieve the right balance between lecture style learning and hands-on practical learning. So it's not a case of always lectures lots of hours in the week and learning from books. That's obviously very important, but it's also equally important to translate those skills, what you've learned in the theory, in a practical sense, which any young engineer would do. And being able to get hands-on with whether it's the pilot plant here or in undergraduate lab facilities, it's a really good opportunity, I think. So we're very fortunate that Colin has very kindly agreed to provide us a tour of the plant. Being the plant manager and the expert in our department, we're very much looking forward to this. So Colin, whenever you're ready, please do lead the way.
Okay, so I'll now take you around the plant area. Okay, so now we're in the main control room. This is the area that we operate the process facility from, which I'll take you into shortly. As I'd mentioned earlier, this goes over 4 floors of the building. So we have 2 main columns where we do the processing for our gas, and the way that that works is actually relatively simple. What we're doing to remove carbon dioxide from a mix of other gases is take advantage of the properties of carbon dioxide when it gets wet. When carbon dioxide gets wet, it becomes slightly acidic, so we can use an alkaline solution to remove it from that mix of other gases. And the basic process that we use is really is this one. So what we're doing in this particular case is we feed our carbon dioxide rich gas into a column on the right hand side, which we call an absorber. That gas flows from the bottom to the top of the column, and to catch the carbon dioxide from that gas we feed in a alkaline solution, in this particular case something called monoethanol MEA. The key thing to remember though is that this is just an acid-base reaction in its simplest terms. So because the solution reacts with the carbon dioxide, we remove that from the gas mixture. Clean gas, or a lean gas as it's called, comes off of the top, and that can then be released to atmosphere. The carbon dioxide is captured in the liquid because it's reacted with it. Now needs to be released from that liquid in a controlled way, and the way that we do that actually is to heat the solution up. So in effect we're boiling the carbon dioxide out of the solution. Of course what we're doing in practice is we're shifting the equilibrium for the reaction slightly. We need to provide that heat energy. So to provide the heat energy, actually we use the hot liquid coming from the bottom of the other column to warm up the cold stuff feeding in. And we actually need to achieve a temperature of typically around 110, 115 degrees C. So we may need a little bit more heat. That's provided by what we call a reboiler, and that's heated by the, in our case, the college steam supply. On a power station it would be the same sort of thing. Because of the temperature in our desorber column, as it's called, the column on the left hand side, the carbon dioxide starts to get released, but we may also generate water vapour from our solution. So we then need to clean the stream that comes from the top of that column, and the way we do that is pass the fluids through a condenser so that we form liquid that we can separate off and put back into the column, in this case predominantly water. The carbon dioxide we then take off to do other things with it. So that's the basic process, and if you think about this particular process, it's really a figure of 8 loop between 2 columns. One operates at around 40 degrees C, that's where we capture carbon dioxide, and the other one operates at around 110, 115 degrees C. That's where we release the carbon dioxide from its solution in a controlled way. That's the simplified version of the diagram. Actually, this is the area that we use in the control room, so this represents exactly the same thing. In terms of our mixture of gases, we feed those in at the bottom right hand corner of the diagram, and they then flow into the bottom of the column on the right hand side. When we go into the plant area later, I'll point out to you which of those columns it is. The solution that we use to capture it feeds in at the top and trickles down through it, so that's where we're catching our carbon dioxide. Clean gas comes off at the top, we dry it up a little bit, and then we can release it to atmosphere exactly like you do on a much bigger scale process. But for teaching purposes, we cycle most of it back to the start again. For the carbon dioxide that's been captured in the liquid, we take the liquid from the bottom of this column and then feed it into the top of the column on the left hand side. We need to heat that solution, as I've mentioned, to release the carbon dioxide, and to provide that heat energy we use the hot fluid from the bottom of this column to warm up the cold stuff going in. We need the additional heating, so this is where we get our additional heating from, and that's the part that's supplied by the steam supply from the college. On the top of this column, the carbon dioxide will be released, and we'll also generate some water vapour from our solution, so we need to pass that fluid through our condenser, which is labelled as C400 in this case. The liquid we form, we put back in the column. The carbon dioxide, we dry up a little bit more. And in our particular case, again, we want to reuse it, so we cycle it all the way back to the start again. On a bigger scale process, around this area, you take the carbon dioxide, put it into a pipeline network, and perhaps use it for other things. Not so many oil wells in the middle of South Kensington that we could pump it into, so actually we recycle it back around. Okay, so we're now on the second floor of the process plant. We're actually looking at the right hand side of the process that I described earlier up in the control room. So in this particular case, this is where we feed our gas mixture in. The carbon dioxide feeds in on the top pipe and then goes through there. Our nitrogen supply feeds in on the bottom, and that means we can vary the proportions so we can replicate the gases coming from either a coal-fired power station or a gas-fired power station. This mixture of gases then flows around through some pipes into this vessel, where they get mixed up a little bit better and also mixed up with some of the gases that we reuse. And then from the top of that vessel, those gases go into the bottom of the column just in the background. That column goes to the very top floor of the process plant, so the gas flows from the bottom to the top. The solution that we use to capture it feeds in at the top and trickles down through. That's where we're catching the carbon dioxide. Our clean gas, our nitrogen in our particular case, we dry up on the top floor, which we'll go to see shortly. And once we've dried it, in our particular case, we want to reuse it. So we bring it back through the left-hand vertical pipe as you're looking at things, and then cycle it back to the start again. The carbon dioxide that's been captured in the liquid gets pumped from the bottom of that column through towards the top of the column on the left-hand side, which I'll show you shortly. As we do that, we need to heat it to enable us to release the carbon dioxide from the solution. Okay, so we're now on the left-hand side of the process plant that I was describing earlier in the control room. What we do is the liquid that has captured carbon dioxide gets pumped from the far side in your background across through the blue rectangular frame just in front of me, which is what we call a plate and frame heat exchanger. In there, that liquid gets heated, and once it's been heated, it then goes through this bigger diameter silver pipe to the very top floor of the process, which we'll see shortly. That enables us to heat the liquid to around 85-90 degrees C, but we still need some additional heating to enable us to release the carbon dioxide completely from the solution. So what we then do is we use this component, which is called a thermosiphon reboiler. That's heated by the site steam supply. That provides us with our additional heating that we require. So once that's operating together with the blue rectangular frame, the plate and frame exchanger, then that provides us with enough temperature in this column to enable us to release the carbon dioxide from our solution. On the top floor, that carbon dioxide that is released from the liquid gets dried up further, and in our particular case we want to recycle it, so we then bring it back and over to the start that I showed you previously again. Okay, so we're now on the top floor of the process. This is the gas handling part of the process, but we're looking at the plant from the reverse side. This is the stripping column, or desorber column as it's called. That's where we release the carbon dioxide from the solution. So normally that would be running at very high temperatures, around 110, 115 degrees C. The liquid that we need to feed in to get the carbon dioxide out of feeds in a pipe just there from those pipes that I pointed out to you earlier, and falls down through the column. Because of the temperature, the carbon dioxide starts to get released. It comes from the very top of the column, but we may also generate some water vapours, so we need to separate those streams out a little bit. And that's actually what this unit just is for. That's the condenser that I talked about when we went through the flow description. In there, we cool things down, and that enables us to change the water vapour back to liquid, so we can separate the liquid, put it back into the column. The carbon dioxide, we dry up a little bit further, and then in our particular case, we cycle it all the way back down to the very ground floor and the start of the process. So that's the stripping part of the process. The clean MEA solution comes in to this column, which is the absorber column, and that one feeds in on the top floor of the process. In this case, this is the MEA solution is released. It's got no carbon dioxide in it, and that comes in and falls down through the column, so we can catch more carbon dioxide. This one runs at a lower temperature. The clean gas comes off at the top and then goes into this separator to make sure we've got no liquid in it. The nitrogen we then pass back down to the ground floor again so we can reuse it. The liquid goes back into the column, and that's the overall process. That's the figure of 8 part of the process.
So thank you, Colin, for a very insightful tour of the plant too, and it was really great to see the plant up close, and especially on the different floors as well, to get an overview of the process. I hope the audience found that very useful as well, and probably encourage you to join our department at some point and visit these impressive facilities. So, as you know, in ChemEng Conversations, we like to get to know our guests more on a personal level as well as an academic. So we thought it would be a great idea to get to know Colin Hale outside of the pilot plant, which doesn't happen very often, but we'll give it a go anyway. That's okay with you? So, what do you like to do in your spare time?
Actually, in my spare time, I quite like going to concerts and things. So last year, I managed to go to see Linkin Park, which was really good, near to the front of the
Nice, very nice.
front of the stage. Guns N' Roses, a bit before that.
Okay.
Coldplay from time to time. So I quite enjoy doing those sorts of concerts, actually.
Oh, that's great. So you're quite a big music fan.
Yeah, definitely.
Do you like to travel?
I enjoy travelling, and I've been lucky enough both through the research position I had before and more generally to travel quite widely. So I spent a month travelling around Brazil, for example.
Mm-hmm.
That's actually one of the ways that I learnt my Portuguese. I've forgotten quite a lot now, but I'd got to the point where when I was travelling around Brazil, the Brazilians knew I wasn't from Brazil, but they didn't realise I was from the UK, which I thought was quite an achievement.
Oh, that's really impressive. And Portuguese is quite a difficult language, so you managed to... How long were you there in Brazil?
So that was a month travelling around, actually. So during that month of travel, I went through Rio de Janeiro, then further south to a place called Florianopolis, which is a little island off of the coast of Brazil connected by a bridge, into the middle to a place called Belo Horizonte, and then across to Foz de Iguaçu, so Iguaçu Falls, which is the second highest and second widest waterfall in the world, actually.
Wow.
So if ever you get a chance to go to Brazil, that's the place to go.
Okay, definitely. I'll keep that in mind. If I do go to Brazil, I will drop by.
And then from there back to Sao Paulo, and then up to Salvador, which is got a more African influence, but it's still within Brazil. And that's a very picturesque city, actually. So that was good fun.
A lot of travelling tips just there for anyone who's considering going to Brazil. So you've been, as you said, you've been travelling quite a lot, and you've managed to pick up some Portuguese. And you said you have quite a lot of international students in the department as well. So which countries did you say you've had students from the past? So within our undergraduate year, actually, it's a very multinational mix of students. So I think overall we've pretty much had students from every country you can imagine. So we have quite a number of overseas students from places like China, Singapore, Malaysia. For some of the summer school programs that we do, we have students come from American universities actually to work on the plant facilities. The students from China, the students from Korea, students from Mexico. Think of a country, and probably at some point most likely
we've taught some of those students.
And how many, just a rough number, how many people have you had through the through the pilot plant since?
So since we refurbished the plant facilities, then these days it's up to nearly 1,000 students per year come through with various descriptions.
Yeah.
The earlier years it was a little bit less than that,
Mhm.
but overall the plant opened officially April 2012, so probably somewhere around 5,000 students have been through the plant in various guises.
Wow, that's amazing. And I guess one question I'd like to ask you is, what did you always know you wanted to be a chemical engineer?
I guess like many students doing their A-levels or their IB, I knew that I had an interest in science and engineering type things, so I did the typical sort of combination of courses, so maths, physics and chemistry. I decided I didn't really want to go into pure chemistry, and I wanted to apply things. I actually wanted to do things on a bigger scale, actually. So that's really why I started to look at doing chemical engineering. So it sort of developed from some of the interests I had previously.
Okay, that's interesting. And the next question I'm going to ask actually is a request from one of our team members at Chemistry Conversations. Since we asked Professor Omar Matar in episode 1 this question, I think I'll pose this to you as well. So if you had the chance, maybe you've just finished a week, hard week in the plant, and you're going for dinner, who would your dream dinner companion be? You can choose either scientific or non-scientific.
Okay, so my non-scientific dream dinner date actually would be Natalie Portman, and the reason for this is because at one point one of the things that occurred in the plant was the location team for one of the Pinewood movies came here to view this location as a potential site for filming a Pinewood movie.
No way.
Natalie Portman was the star for that movie. As it turned out, the set didn't quite work for that particular movie, but it would be nice to catch up with her just to see actually how she got on the particular film and find out a little bit more about that side of things.
Ah, of course. That's a good answer. And who knows, maybe she has an interest in science and engineering as well.
Well, hopefully.
Yeah, exactly. So that's great. Now, aside from your research, I know you have a strong passion for teaching, and you love to interact with students. And if I speak to anyone in the department, whether it be first year to fourth year or PhD student, postdoc, even the staff members, the only things I always hear is, oh, Colin, he's such a kind guy. He's always there to help us. Always has his door open. Anytime we're stuck with something, we can ask him for help, provide support wherever he can, and including myself. I mean, I've been at your door a couple of times during my undergrads, and it's helped a lot for me as well. So thank you for that. And what is it that you enjoy interacting most with students?
I'm lucky to actually have two slightly different roles because I enjoy doing the lecturing to bigger groups of students, but in a lecture you don't get to know the students so well. With projects like the ones in the pilot plant area and in the laboratory facilities, for example, you really do get to know the students very, very well on a much more personal level, and I think that's really important, actually.
Mm-hmm.
So one of the key things is when, of course, our students come initially, maybe they're a little bit lost, and you can see them develop very, very quickly over a period of time. So by the end of the fourth year, they're confident to tackle any problem globally, and not only tackle it, but also lead in the challenge to meet those problems.
Yeah, absolutely, and that's essentially what you want at the end of your degree.
Yes,
once you leave.
Exactly. So that gives me quite a big sense of achievement. Actually.
Yeah, I can imagine. And last question for our conversation would be, since you've been here at Imperial for both your undergraduate and postgraduate studies, what advice would you give to the students who are going through the process from your experience so far?
Okay, so as you rightly pointed out, I went through the undergraduate program some time ago and then followed on and did my PhD here. For the undergraduates amongst you, then I think one of the key things is try to maintain a consistent effort all the way through, but remember that although the chemical engineering course can be quite challenging sometimes, it's also important to have quite a good balance between the work things and the social aspects.
Absolutely.
For PhD students, of course, you've got a longer term project in those cases. And I think one of the key things to remember for that is when it comes to research, If it worked first time perfectly, you've probably done something wrong. One of the key things is research by its nature tends to be quite challenging, and you will go through cycles where for some time things won't work very well. But then actually, if you keep persevering, over time what you'll find is that you'll get to the result that you needed, and that's a real sense of achievement. So it's a bit of a roller coaster ride sometimes. If you remember that, I think actually that's the best way of tackling a PhD.
Oh, that's definitely very valuable advice, Colin. Thank you very much. It's been a pleasure having you on the show. So thank you very much for your time. It's been a pleasure. So that's all we have time for this episode of Chem Eng Conversations. It was a pleasure to talk to Colin Hale today inside the pilot plant. If you'd like to catch up with all of the previous episodes of Chem Eng Conversations, please do visit our YouTube channel and departmental website. All of the details are on your screen. As always, we'd love to hear from you, so please do engage with us on social media using hashtag #CEConversations. We'd love to hear from you as always and get your feedback. We hope to provide you with many more exciting episodes of Chem Eng Conversations soon, but until then, from my team and I, it's thank you and see you soon.